So yeah, for the next hour, we'll talk about NSX Advanced Architecture Concept. I'm Dimitri.
And I'm Yasin.
And we're both part of this NSX business unit because, as you know, VMware does more than compute, does also networking. And so we're part of this division. And this one is actually a follow-up of the session I did, not with Andrew, but with Kevin. So that's not the latest deck, my bad. We'll see if some bad stuff happens later. But anyway, so yesterday we did a session which is an introduction on NSX-T, which is a new edition of NSX. Who attended this one yesterday? Yeah, cool, like almost 80%, 85%. So for the other 15%, I won't repeat what we talked about yesterday, just 5 seconds so you're not completely lost. So we have in VMware NSX. Oh, who knows NSX first? When I say NSX, okay, everybody. Who is using NSX? Like 50%-ish, a little bit more actually than 50%. Okay, so that's cool. We have now 2 NSX editions. So I'm sure all of you are using the edition NSX-V, which is NSX for vSphere, which is definitely the best product when you have the whole VMware stack. So you're a VMware addict, you have the whole SDDC with vCenter, ESX, VRA, VRO, and it's great. And NSX-V is the best solution to provide the best network and security services for you. But we also have to acknowledge, maybe not too much here, because you're at VMworld, but as VMware, we have to acknowledge the world is not run by VMware. Some people, for some odd reasons, don't use VMware everywhere. So we want NSX everywhere to provide the best network and security services for everybody, even those crazy people who don't run VMware everywhere. And that's why we have this edition, NSX-T, okay? And that's what I presented, and we did a lot of live demos on how to create network and security services on ESX, on KVM, and we use a cloud management system, which is not VRA, which is OpenStack, because NSX-T edition can be driven by any cloud management platform. There is an open API, so we used OpenStack to deploy a 3-tier architecture deployment in 1 click. So if you didn't watch this, for the 15% of you, watch this, it's pretty cool. Now, this session is about explaining what happens behind, how the magic, what is the magic behind to be able to provide those services, okay? So I hope some of you are geeks because we'll go quite deep. So if you're marketing guys, you can save 1 hour and go. Okay. Nobody's leaving, so I guess, okay, all of you are quite technical. So let's start. I'll do the architecture and the switching, and Yasin will do routing. So I stop at layer 2. I guess I'm not a real geek. So, okay, the architecture. Everybody knows NSX, which I mean NSX for vSphere, the edition NSX for vSphere. It's very, very similar. So I'll go fast on this. You have any platform, any infrastructure. So the Cisco you love, the Juniper you love, the HP you love, Arista, Dell, I love them all as well. I don't care. It's completely decoupled, this NSX-T edition, like the NSX-V edition. We just require a fabric with IP connectivity, so my hypervisors, ESX, KVM. Yeah, KVM is not a bad word. It's the only room you can say this word, by the way. They just have IP connectivity, and that's cool. So now what are the data plane elements? That's your hypervisors, ESX, KVM, with NSX bits inside. And the NSX edge, which is an element, it's not a, it's an NSX element that will provide the north-south communication to go from the physical world to my logical world, to my overlay network. And it can be done via L3, or it can be done via L2, if you have some VMs on my logical switch, on my logical world, 10.10.10.10, talking to a physical server in the same subnet on a physical VLAN, 10.10.10.11. In that case, for L2, it's this element. For L3, it's this element. And this element, NSX Edge, provides you the north-south, as I said, L3, but also advanced services like the load balancing, which is not available today, but it's coming very shortly after. Okay, so that's the data plane. Then you have the control plane, and the control plane are the elements. It's a cluster for high availability and massive scale, because they run in an active fashion. And those guys are in charge of pushing information to the data plane nodes on where is what and what to do when a packet arrives. We'll talk about that in a few minutes. But those ones are not in charge of processing packets. The data plane, the VM traffic or the external traffic talking to the elements, the VMs in the logical world, there is no data packets processed by those. Everything is done in the data plane elements. And the last one, the management plane, is where you do your UI click to create your logical switch, your logical router, your firewall, and so on and so forth. That's where you go, and that's the one that has the configuration, and it will push the configuration to the control plane that will push the configuration to the real elements doing the real job. And you can do click all day long to create stuff. Or you can automate that, because 100% of NSX is available via an open API. So you can automate that, and that's what I told you 5 minutes ago, where we demonstrated an open stack where one click and boom, you have a bunch of VMs, a bunch of switches, routers, firewall, and so on and so forth. Okay, in one single click. Makes sense? So it's actually, that slide could be used for NSX-V. It's exactly the same architecture. The tiny difference is, oh, there is this KVM here, which obviously you don't have on NSX-V. And all those are the NSX elements. So, usually I explain stuff, explaining the theory, and then I do a demo. Let me do it another way this time. I'll start with the demo, and I'll explain what happens in the backend. To save time, because we have a lot of content, it's not live. It's recorded. I love to do live, but it takes longer, so I have this recorded. So I log on my NSX-T manager, and you can see I have a couple of ESX, a couple of KVM, and I create a switch, and I do it in this demo via the UI directly. And now when I do this, the switch is created and is known by all the hypervisors. And I'm showing you now ESX, and I'll show you KVM in a minute. So I go on my vCenter 1, and from vCenter 1 now I see this NSX logical switch, and I plug my VM on that logical switch, and you can see now it's plugged on the logical switch. I do the same on vCenter 2, and here we go. From vCenter 2, on another ESX2, I plug it, and now I have this. You can see it's another difference with the NSX-V edition. Here I have two different vCenters. So NSX-T is not tied one-to-one with one NSX, one vCenter. It supports multi-vCenter. It also supports actually no vCenter at all. You can have no vCenter and directly do stuff on ESX. Of course, you lose all the benefits of vCenter with the DRS, the vMotion, and all the beauty of vCenter, and that's why you buy it. But if you want to, you can also do it without any vCenter. Okay? So I'm still quite high level. Oh yeah, here I'll show you a ping. It's not the most sexy demo, but yeah, here I log on my web 1 and I ping my web 2, and woo, beautiful, the ping is working. Okay, let's see what really happens in the backend. So that's where the marketing guy can sleep. So what I did is I logged on the manager, and I created the switch. What happened when I did this, create the switch, click OK, the manager talked to the ESX and told, first the manager saved that information on persistent storage. So now the NSX manager knows about this logical switch and gives the information to all the ESX. You remember in the video, you can see all the hypervisors NSX manage for the network and security. And so it pushes this information to all the ESX. So now the ESX knows about it, and the vCenters know about it. Then I went on vCenter, I plugged my VM1 on the NSX logical switch, and what happened at that time, the ESX talked to the manager to say, hey, I have this VM, VNIC, so we call that a VIF, virtual interface, So ESX1 told the manager, I have this VM1, not this VM1, sorry, but this VIF, this VM VNIC, connected to logical switch web LS. So now the manager will create a logical switch port that is attached to that VNIC, to that VIF. So logical interface at the logical switch port to the VNIC virtual interface. And the manager will tell that to all the controllers because they work in an active fashion. But for massive scale, what the controllers do, they elect a boss for that specific logical switch. Now, if you have hundreds or thousands of logical switches, some logical switches will be managed by controller 1, some by controller 2, some by controller 3, and another one will be the backup. But they really run on in an active fashion. But for logical switch 1, let's say controller 1 is in charge. So he's the boss of logical switch 1, and all the hypervisors talk to the controller. They have a persistent connection. So the ESX told the controller it has VIF1, the VMNIC VIF1, and the controller knows from the manager VIF1 is connected to LIF1, to the logical switch port 1, and gives this information to the ESX. So now the ESX plugs the VMVNIC VIF1 to the logical switch port LIF1, and it has this information inside the ESX1. And in the chat between the two, ESX1 gave the information about the MAC address, because ESX knows the MAC address of the VM. ESX told the MAC address of VM1, of the VMNIC VM1. So now the controller knows MAC1 is on ESX1, the IP address, the TEP, transport interface, transport endpoint. So the IP address of the ESX. MAC1 is on ESX1. So controller knows that and is happy. And when I did plug the VM2 on the same logical switch, same thing happens. Okay? So at the end of the day, the controller 1 knows MAC1 is on TEP on ESX1 and MAC2 is on ESX2. And then I did a ping. So before doing a ping, each ESX is aware of its local VMs connected to the NSX switches, but not the other people. There is no push information on ESX. We'll see how it works on KVM. But on ESX, it's like this. So when Web 2 wants to talk to Web 1, it sends a packet of ping with the destination MAC of Web 1, and it goes to ESX2 NSX vSwitch. And it doesn't know where is MAC1, so it will ask the controller, hey, please give me where is MAC1, and the controller will say MAC1 is on ESX1. And it adds this information in its local MAC table for LS1, and will encapsulate that, send it. The ESX1 will remove the encapsulation and send it. So the physical world will see the IP address of ESX2 to ESX1. They can be in different subnets, who cares? They don't have to be the ESX IP addresses in the same subnet. And the Web 1 will receive the real packet, exactly the same packet sent by Web 2, so they don't know anything about the NSX underneath. They believe they are on the same switch. Actually, they don't know they are VMs. They believe they are on physical servers connected to the same physical switch. Okay? Make sense? Yeah. We'll talk about it. So the question is, if for whatever reason the controller doesn't know the MAC address MAC1, because for whatever reason, I'll talk about that in a minute, in 3 minutes. Okay? We won't have, oh yeah, questions are at the end, but okay, let's finish with this.
What was the ARP?
The ARP, it's a good question. Here I assume the Web 2 did an ARP request and knows the MAC address of IP Web 1. So the ARP, actually I don't show it, I should show it. I didn't because I was afraid to run out of time, and I may. So quickly, because you asked. When there is an ARP request, there is also an ARP table for logical switch 1, and this one it doesn't know at the beginning, so it will ask the controller, and the controller has the information, and the controller, same thing. Okay? Okay, for KVM. So, who is using KVM here? Don't be shy. Hey, 5 people. Okay. So for you, the others you can sleep. So for KVM, it works a little bit differently. Let's go with this. So first, there is no vCenter, obviously, managing KVM. So you have to get the information of the VIF, the UUID, the VM3 VNIC information. So you get it in the XML file of Web3, and you go on NSX, and you create the port yourself on NSX. Now, if you have some automation tool like OpenStack, obviously you don't do that. I'm in the case where you do everything manually. There is no orchestration on the top. So with this information, I create directly on NSX, which is something I did not do with ESX. I create the port, the logical switch port, and I create that port on that switch, and I attach with the VIF, blah, 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 this friendly name. And now I have the port that is created and connected to the VIF, and that's what I have in the logical space. Now, what really happens, oh yeah, and I do a beautiful ping. Okay, let's keep this. You've seen a ping in your life. Okay. What really happened is this. So I went on the NSX manager and created the LIF VIF attachment, so a new logical switch port connected to the VIF. And when you did that on the NSX manager again pushed that information to the controllers, all of them. So all the controllers have this information, but controller 1 is the one in charge of this. And KVM1 has a persistent connection to the controller 1, like the ESX. So KVM1 told controller 1, hey, I'm the one with VIF3. The friendly name UUID like this. So controller 1, when it received this information, VIF3 should be attached to logical switch port LIF3. The controller 1 told that information to KVM1, and KVM1 plugged it like this to the LIF3. Okay? And KVM1 told controller 1 about the MAC address of Web3. So now the controller has this information, okay? But unlike ESX, where ESX we don't need to do the push, we ask for the ESX to pull the information when needed. On KVM we cannot do that because the logical switch the NSX switch on KVM is actually Open vSwitch OVS. I don't know if you've heard about it. It's a programmable switch. And there is no pull information available on this KVM NSX switch. So the controller push the information, and the controller will tell KVM1, you know what? MAC1 is on ESX1 IP address, and MAC2 is on ESX2 IP address. So what happens when you do the ping? When you do the ping, Web3, I skip the ARP request, but same thing happens for the ARP request. The Web3 send a packet to MAC1. KVM has already the information. MAC1 is behind TEP1, ESX1, and then it will send it encapsulated and de-encapsulate on ESX1 and send it to Web1. Okay? Now, back to your question. Let's say Web3 talks to a MAC address, which is MAC 15, which is unknown by the controller. What could be the reason? Usually it should not happen really, because the controller has a persistent connection to all the hypervisors, ESX and KVM, and they report the MAC address of their VM. So this should not happen. It should happen only in the case where you have a logical switch in my world, which is bridged to a VLAN in the physical world, not my world, and Web3 10.10.10.10 wants to talk to physical server 10.10.10.50, and obviously controller doesn't know about 50 because 50 is not in his world. So when does that happen? It happens for broadcast other than ARP request, broadcast, unknown unicast, and multicast. So for bump traffic, then when the hypervisor asks the controller, hey, where is that stuff? The controller will say, hey, I don't know. And then the hypervisor will flood this to all the hypervisors. And let's say you have 500 hypervisors, but only on this specific logical switch you have stuff connected, VMs connected, on 20 of them out of the 500. This flood won't go to the 500 because there is no point of sending traffic to a hypervisor that has nothing connected to that logical switch. So the goal is to send that BUM traffic, unknown traffic, to the, what did I say, the 10 hypervisors only. And how do we do that? How do we do that? So we have, let me speed up. We have, let's say, hypervisors in different subnets. So I'm talking about hypervisors, ESX KVM, the real IP address of the ESX KVM, nothing to do with the IP address of the VM. And let's say you have a leaf and spine or whatever architecture, but they are in different subnets. You have some hypervisors in the subnet 192.168.1.0/24, some hypervisors in another subnet, some hypervisors in another subnet. How do we do the flooding to the hypervisors we have to talk to? When it's inside your own subnet, and this you know that because you know your IP address, you know the range, so you know those ESX KVM are inside your own subnet, then for the BUM traffic, you send them directly. So one packet here, one packet here. Assuming hypervisor 2 and hypervisor 3 have stuff on this logical switch. Then for the hypervisors 4 and 5, which have stuff on the logical switch, but not 6. In my example, hypervisor 6 doesn't have anything plugged on logical switch 1. Then only one packet will go out, and this ESX KVM or KVM will do the local replication. Okay? So for each subnet, for your own subnet, you do the replication yourself. For the other subnets, there is an election, and one guy would be in charge of doing the replication for each subnet. And for logical switch 1, in my example, it's hypervisor 4, which is in charge of this replication for logical switch 1 for subnet B. But for subnet, for logical switch 2, it's maybe hypervisor 5. It's not like hypervisor 4 is in charge for everything. Yeah, it's always unicast here. It's always unicast everywhere, actually. But keep your question, because I may answer on that slide, and I will really run late, and he scares me. So how do we do this? I have only 2 minutes left. Let's do it. So hypervisor 1 send this multicast packet or unknown unicast packet, whatever. So you have the real packet sent by the VM and the payload. In front of it, it will be the IP address of ESX1 going to the IP address of KVM2. And KVM2 will receive it and will send it to the VMs connected to that logical switch. That's for the stuff inside the hypervisors inside your subnet. Okay? When it will receive this, this guy, there is data plane learning as well. This hypervisor 2, ESX or KVM, will learn that the MAC address of Web 1 is behind hypervisor 1 because it's coming from hypervisor 1. So obviously, for sure Mac 1 is behind this hypervisor. Now in case I send it to hypervisor 4 and hypervisor 4 has to do the local replication in subnet B. Same thing, I send it to hypervisor 4 and hypervisor 4 send it to hypervisor 5. But in that case, hypervisor 5 will see traffic coming from hypervisor 4. And if we don't do any magic, hypervisor 5 will believe that Mac 1 is behind or is inside hypervisor 4. So how do we work around this? When hypervisor 4 receives this, it adds some information in the overlay, in the encapsulation, to say, hey, you know what? The source of this packet is not me, it's actually hypervisor 1. So this guy, hypervisor 5, knows Mac 1 is behind hypervisor 1. So what I try to say in this too long explanation is that in the overlay, we add information. And I use the word overlay and not VXLAN because actually this is not VXLAN. And why is it is not VXLAN? Because in VXLAN you have only 8 bytes to say something, to add some information. And 8 bytes is not enough for this example, and it's not enough for many other things we do. Like for the people here, yesterday, we did the trace flow. I don't know if you remember, where it's a pretty awesome tool, operation management troubleshooting tool. And we need to write stuff in the payload. We can go in details if you want later. But we need space. And that's why we don't use VXLAN, we use Geneve. And Geneve is not standardized yet. It's still a draft. You can look at if you're really a real geek, you can look at the draft. But that said, you have everybody behind. You have Cisco, you have Intel, you have Broadcom, you have pretty much everybody. So the new standard will be this. And if you look at other people doing network virtualization, like Cisco, for instance, actually Cisco has the same challenge. So they don't use VXLAN, they use a proprietary VXLAN. And what is this proprietary VXLAN? It's VXLAN, but with a bigger payload where they can add their own blah blah information because they need to provide some extra information to do some fancy stuff as well. But they don't use VXLAN. So people actually, even if VXLAN is a standard, very few people use real VXLAN. And I don't know about Cisco, talk to them if they are your friends, but I'm happy to take a $100 bet. They will move also to Geneve because this one is a real standard that will be really used by everybody. Okay? We are the first vendor using it, but I'm sure other people will use that. And now you understand why we use this. Okay, that said, I'm 4 minutes late, and let's talk about routing.
Yeah, so it's always fun.
Thank you. Wow.
It's always fun watching Dimitri presenting, even if you don't care about NSX. Okay, I saw how many people have experience and knowledge for NSX for VMware. So I would like to ask you, please forget everything that you know for this section. So it will avoid a lot of confusions. I will try to compare where it is possible, but in general there are many differences. I will go with quick example. So usually the power of NSX-T is to be automated. So the best way to provision networking security routers is through some cloud management platform or some automation tools. So the best examples are OpenStack, VMware integrated OpenStack or any other OpenStack, or Kubernetes or any other cloud container management solution. Also, we have fully supported SDKs for NSX-T. These are VMware supported that you can use to automate the stuff. Anyway, here in this example, we are doing everything manual. And we have 2 virtual machines connected to the 2 virtual switches that Dimitri did. So I would like to add a router and to connect these 2 logical switches to the router. So you see that there are 2 kinds of routers, T0 and T1. I will go in details about the difference a bit later. But here I create new router port and I connect this port to my web logical switch. I just give a name to the port. And I will put the IP address of this router. This will act as a default gateway for my web server 1. So as a next step, we need to do the same for the application logical switch. the reason we are doing that is because it is, before start automating the things, it is good to see how to do it manual. So you see, right now we have one tenant router connected to the two logical switches. And I will log into my application VM, and will trace my web VM, and you will see that the traffic flows through this new router between the two. And for those of you that have attended yesterday's session, maybe it will not be interesting, but yeah, I would like to show you again this nice visibility tool. We have many of those. So if you don't have access to the virtual machine itself, you can use from the graphical interface of NSX this trace flow tool that will show you end-to-end the packet flow between hypervisors with a lot of information. So in this case it is successful, but if by some reason the packet is dropped, you will see exactly the place where the packet is dropped. If it is firewall, you will see the firewall row ID where it drops this packet. Okay, for the edges. So this is the main difference between NSX-T and NSX-V. In NSX-V you have edge or ESG that keeps the routing with the physical world. With NSX-T, edge is just a container of resources. So it could be either bare metal or VM form factor. So, but the edge here is just to hold some of the components of the real routing components, and I will go into details about the routing components a bit later. So everything that is for routing is distributed, and everything that requires stateful services like NAT, DHCP, edge firewall, we have both distributed firewall and edge firewall on the routers. So these functionalities are hosted on this edge, either bare metal or VM form factor device. So you can form cluster of edges. So you can have up to 8 edges per cluster. So you can imagine when it is bare metal, the performance is significantly higher.
When we say high, it's like 80 gig of traffic out of the single server. That's a lot of traffic. Yeah. DPDK just changed the world in terms of software routing.
Yeah. So the edge is just a holder for the routing components, and we have 2 tiers of routing here. It is a bit different than what we have in NSX-V. We have something called T0 router, and this is typically, we call it provider router. So the T0 router is the one that you need to manually go and configure at the beginning when you install your NSX. So you need to configure the BGP neighborship with the physical world. So this needs to be pre-configured before you start automating the things. And we have T1 routers. Usually the T1 routers are the ones that are dynamically provisioned by some provisioning system like OpenStack, Kubernetes, or whatever. So, for example, when you configure this system, let's say OpenStack, you need to specify the ID of the T0, so OpenStack will know how to connect the T1 routers to this T0. And what is interesting here is we don't have dynamic routing between the T1 and the T0. So the routing between these 2 routers is handled by the controllers. So if you want to advertise to the physical world anything specific, let's say NAT or connected routes or whatever, you need to configure this on the T0 router, and T0 router will learn the routes from the T1 router. Okay, and now next slide is a bit difficult to explain, but I will try. Every component, every router, no matter it is T0 or T1, I call it logical router, have also 2 components, distributed router component and service router component. So I will call them DR and SR for short. So T0 has DR and SR, and T1 has DR and SR. And the DR component is on every transport node, so this means every hypervisor that is managed by NSX. And the SR is the piece of software that sits on the edge itself. So every stateful service goes to the SR component, which sits on the edge, and the routing happens on the DR component, which is distributed everywhere. And why we are doing this, I think this slide will show you more details. So in this example here, we have one T0 router, which is the provider router, and one tenant router, T1 router. You can see both the T0 and the T1 have distributed router component on all hosts. So on this side, on the right side, we have hypervisors. On the other side, we have edge nodes. So we have the distributed router component everywhere. And we have the service router component just on the edges. So in this particular example, there is no stateful services on the tenant router, on the T1 router. So this is the reason there is no SR component for the T1 router. So the routing happens on the DR components. The stateful services are forwarded to the edge cluster. And does it make sense? Okay, I have several more slides showing the traffic path, and I think this will help you understand why we are doing it that way. So let's take for an example this topology. So we have T0 router connected to the physical world, and we have two tenant routers, tenant A and tenant B, and every tenant router has two logical switches and one virtual machine per logical switch. So yeah, I will try to show you different examples what happens when two virtual machines, or in NSX-T containers, pods, whatever, try to communicate to each other. So in this particular example, we have two virtual machines in the same tenant. This means behind the same T1 router, in the same host, and when VM1 tries to reach VM2, the traffic goes out from the VNIC, reach the distributed router component of the T1 router, and the distributed router component of the T1 router sees that the destination IP address is directly connected to it. So it's easy, the traffic goes directly inside the hypervisor. The same example, but if the destination virtual machine is on another host, pretty much the same. So it gets to the distributed router component of the tenant T1 router, and it is directly connected, but the DR router sees that the destination virtual machine is not on the same hypervisor. So it sends the traffic to the VTAP. It is GNIF encapsulated and go directly to the destination virtual machine. You can see the routing happens just on the source hypervisor. So on the destination, there is no routing. Okay, this is more interesting. So we have communication between tenants. So we have two different tenants. Everyone is behind different T1 router. So you can imagine the T1 routers are always connected to the T0 router. So the routing should happen from T1 to T0 to the destination T1 and then to the destination VM. Usually with the standard approach, these are a lot of hops in your network. But with the example that I gave you, what happens? The VM1 sends the packet, it gets to the distributed router component of its own T1 router. So the T1 router sees that the destination network is not connected to it, and by default sends the packet to the T0 distributed router component. So this is on the same hypervisor. The T0 distributed router components see that the destination IP address is on a logical switch connected to the T1 router to the destination T1 router and sends the traffic locally to it. And the distributed router component of the destination tenant T1 router sees that this is directly connected to it and sends traffic directly to the VM. So you can see in NSX-V, we have DLR that do the distributed router and edge that is always centralized. With NSX-T, we have both layers fully distributed. So far, so good? Okay. The same example, but the destination virtual machine is on separate host. So VM1 sends the traffic out, it gets to the distributed router component of its own tenant router. So it is sent to the T0 distributed router component. The T0 sees that this network is connected to the destination tenant router and sends the traffic there. It is sent to the VTAP, GNIF encapsulated, and goes to the destination. Again, routing happens only on the source. Okay, another example. Ingress from the physical network. And this is where the service router components plays, because if you want to have BGP with the physical world, this happens on the SR component, on the service router, so it cannot be distributed. So the traffic goes on the edge appliance to the SR component of the T0 router, because the T0 router is the provider router. The T0 router sends the traffic to its DR component for distributed routing, and the DR component makes the routing decision and sends the traffic to the DR component on the destination T1 tenant router on the same host, in this example, on the edge. After that, the traffic is GNIF encapsulated and goes to the destination hypervisor where the VM sits on, and the traffic goes directly to the VM.
Can I say one thing? Yeah.
Yep.
So if you understand all of that, that's great. I mean, that means you're a real geek and you have tattoos and you listen hard rock, metal, heavy metal music. But if you're not one of those, don't understand that. You don't have to understand that. The only thing you have to understand is if it's something from the logical world to the logical world, so a VM talking from another VM, and okay, you have routing between the two, they're not in the same subnet, but it will always go from hypervisor 1 to hypervisor 2. Okay, the routing is done distributed completely, and you always go from hypervisor 1 to hypervisor 2. So what is the power, the scale of your routers for east-west communication? That's the scale of your hypervisors. Okay, each hypervisor can saturate a 210 gig NIC. So your router, if you have 100 let's even smaller, 10 hypervisors, how much can you do? 200 gig of routing. If you have 100 hypervisors, now it's 2,000 gig of, okay. So it's really horizontal scale, that's very great. Now if you have to go from the physical world to the logical world, what is the entry point to go north-south from the real world to my world? That's through the edge node. Make sense? Just remember that, and otherwise you can also understand this, but you don't have to.
Yeah, the main point here is to explain how we distribute even the T0 router, because this makes a lot of sense here. I will give you a last example here. So it is egress to the physical world. So if the VM1 wants to communicate with something in the physical world, so it gets to its default gateway, which is tenant 1 distributed router component. So after that, it goes to the T0 distributed router component, because it needs to go to follow the default route and to go outside of the NSX domain. After that, the distributed router component of the T0 sends the traffic to the VTAP for encapsulation, for GNIF encapsulation. And when it reaches the edge itself, it goes to the service router component of the T0 router. So the DR component of T0 sends the traffic GNIF encapsulated to its SR component on the edge. And after that, the traffic goes out.
How do you deal with multicast?
So what kind of multicast? Layer 2 multicast inside the logical switch, we treat it as a broadcast, but at this release we do not support multicast routing. Yeah. So one more optimization that we do, because NSX-T is designed to be highly scalable and with high performance. I just want to show you, for those of you who are aware of VSXi networking stack, we have something called IO chain, which is different points in the networking stack that you can manipulate the packets. With NSX-T, we have two new points in the IO chain, which is flow cache lookup and fast path. So what happens? Slow path and fast path is something that adds some confusions. Slow path is again in kernel, but you have multiple points where the packet should be parsed, right? With NSX-T, just the first packet goes through all points in the I/O chain, and after that it is added in the flow cache database, and every subsequent packet from this flow bypasses all points in the I/O chain. This improves really dramatically the performance of the hosts. I will give you better example. So we have up1 and up2, and we have the physical NIC. So when application 1 sends the first traffic and it goes through the whole I/O chain, any subsequent packet just bypass everything, and it is much faster. The reverse path is exactly the same. And you can see if application 1 wants to communicate with application 2, first packet goes through the whole I/O chain, through the host virtual switch and back. Any subsequent packet bypass all of this. And for those of you who are experienced in troubleshooting ESXi networking stack would ask, okay, if I want to capture the traffic, because with NSX-V we have multiple capture points where you can capture the traffic for troubleshooting. In this case, NSX-T provides its own capturing tooling. Okay, firewall, it will be easy. It is almost the same as NSX-V. Okay, with NSX-T we provide the same micro segmentation capabilities as we do in NSX-V. The difference here is we can provide this micro segmentation not only on ESXi hosts, but KVM as well, and also containers, Kubernetes pods, so everywhere where NSX-T can run. And quick example, so I will show you the Web 1 and Web 3. They are on the same subnet. With the traditional firewall, you cannot restrict the communication between them because they are on the same subnet. And here, I will create a new security group, and I will specify that the membership criteria of this security group is any virtual machine which name starts with web. So once I save this, all virtual machines that I have that contain web in its name will be members of this security group, and you can see my 3 virtual machines are members of this security group. So if I go and apply this security group in some firewall rules, it will be applied to these 3 VMs. And I will do so. So I will add a new rule. I will put some name. So as source, I will specify my new security group that contains all web VMs. And as destination, again, I will specify the same security group. So this means my firewall rule will affect the communication within my web domain. So every web virtual machine, the traffic between them will be dropped in this case. And I will go to, I would like you to remember the firewall rule ID that drops this traffic. It is 1025. So I will go back to my favorite traceFlow tool, and we will retrace the same. You saw previous time it was successful. Now I will retrace it, and it is dropped on the first hop. And you can see, dropped by firewall 1025. So I think this is great tool for troubleshooting. So maybe some of you are aware that with NSX-V, actually for the firewall functionality, the controllers don't play any game. But here with NSX-T, the controllers are a really important part of the game. So when you put a new firewall rule, policies, whatever, this is forwarded to the controllers, and the controllers are the one that calculate the logical objects to IP addresses. So because you specify your firewall rules as you saw as web VMs, but in the reality, in the kernel, the rules should be IP addresses. So the controllers calculate these values and push them back to the data plane to be programmed. Okay, I will give you some more insight how we do this on the ESXi hypervisors. So for the control plane, we have central control plane, the 3 controllers, and we have distributed control plane. So we are distributing even the control plane. So it is not just a central piece of software anymore. So this is for high scalability. And so this LCP is local control plane, and the main agent that is running is NetCPA. We have the same in NSX-V. And all the communication happens via the controllers. For MPA and NSXA, this is just for reporting back to the NSX manager. So there is no, we are not programming anything from the manager directly to the hosts. And okay, maybe this is clear, maybe not, but how we do this for KVM. So KVM, it is Linux box, open source. Everything that you see in blue is open source standard Linux things. So in the kernel level, we do not add anything. So the things that we are using is Open vSwitch kernel module and the standard Linux connection tracking. And also in the user space, we are using OVS vSwitch-D and the standard connection tracking utilities. Everything in yellow is our own proprietary stuff, how to manage the open source solution. So OVS FWD, so the 2 components for firewalling, and NSX agent is for the communicating from the controllers, and it programs down the kernel modules. So this is how we do this on KVM hosts for the guys who have KVM hosts.
For the 5 guys.
Yeah, for the 5 guys that have KVM hosts. Okay. So there are many blogs and places where you can find more information. To be honest, for NSX-T, the information is not a lot, but we are taking care to get more and more. So please keep an eye on this. And yeah, something important, if you want for next year to have similar deep dive sessions, please give us a feedback. So this will help us understand if you like such kind of content in order to know whether to reduce or to increase such content for next year.
Okay, so we have 5
Thanks.
more. Yeah. Thank you. We have 5 more minutes for questions, and we'll stay another 15 minutes here if you want. Yeah, one question. I'll repeat it.
Do you get the same statefulness for the firewalling? Sorry. Do you get the same statefulness for the firewalling on KVM as on VMware?
Yeah, it is completely the same. We are using the connection tracking utility on the Linux kernel to track the states, and we program OpenFlow rules in the Open vSwitch with our proprietary solution on top of it. So it is the same, and you can have both stateful and stateless firewall on NSX-T.
The rule of thumb is, even if, yeah, we have a paycheck from VMware, I cannot deny that, everything we build in NSX is, in terms of features, is available on ESX and KVM. We won't make something like, oh, if you buy vSphere ESX, then I'll give you network and security services plus plus. But for the 5 of you who decided to go with KVM, too bad for you, I'll give you just basic stuff. We won't do that. So everything you see, everything we talk about in terms of feature, whatever if you have ESX or KVM, you'll have them. You'll choose vSphere because of the compute is better than KVM, but not for network reasons. Okay? Oh, network is here, it's better. Sorry.
Thanks.
Yeah, question?
You showed slow pass and fast pass. Are there any restrictions if you do some network security monitoring as a Zeem solution? Or is it all available and traceable?
So we don't have any partner integration solution right now in NSX-T. So right now, if the traffic needs to go out, it goes directly after the first packet goes directly to the fast path. Most probably for later, if we need to add some additional partner solutions that need to inspect the traffic, this kind of traffic will go always through the slow path, but this is just guessing how we are going to do it. For now,
So at the moment you're blind.
yeah, for the moment we do not have any partner integration with NSX-T, but we are working on it. Yeah.
Okay, last question, and then, no, still 3 minutes, yeah.
I have two scalability questions regarding mostly KVM, to be honest. So you mentioned that in KVM there is no push function to push the MAC to TEP. And well basically
no, there is push.
There is no pull.
Yeah.
There is no pull. So you have to push everything. So what happens when I have 200,000 VMs? Will it not overload the...
So if you have 200,000 VMs, are they on the same logical switch? So if you have 200,000 VMs on the same logical switch,
no, it's not possible. So
then you reach our scale limit. Today we scale pretty high, but we don't scale at that limit, so I'm sorry for you. Now, in real life, let's be honest, because if you have a subnet with 200,000 elements, that's what, a /8 or something like that? I mean, that's insane. So what people do is you have multiple subnets, and on that KVM1, you have VMs. How many VMs do you have on your KVM? 20, 50? You don't have 20,000 VMs on a single hypervisor.
It will be different with...
So out of those, let's make it 50. Those 50 VMs you have on KVM1, are they connected to all of them to different switches, or some of them the same? Let's say they are different. So now this KVM1 that has 50 VMs connected to 50 logical switches out of your 5,000 logical switches will receive information only for those 50. Because there is no point of receiving information for the 4,950 other switches, because it has nothing connected to it. There is no point of having this information. Okay? So that's how we scale. We help the hypervisor to scale.
Yeah, and may I add also something? If you remember, I said for the distributed control plane, so we offload a lot of this functionality to the hypervisors themselves. So this helps us to scale really high.
That's to help the controller himself now to scale higher. We don't do everything on the controller. We let the hypervisors do some stuff. We can explain the some stuff if you want on a one-on-one.
And my second scalability question was regarding the bump traffic. Why not multicast?
For multicast? So for multicast, you want to take it?
Because right now you're using head-end replication.
Yeah.
So if I have 1,000 subnets, that's a little bit.
If you have 1,000 subnet, again, so for subnet 1, and let's say you have 100 hypervisors, for subnet 1, logical switch 1, how many out of the 100 hypervisors you have with stuff on logical switch 1, maybe 10, maybe 50, maybe, I don't know, let's say 10, and 90 of those other hypervisors don't have anything connected to logical switch 1. So now this multicast packet will be sent from your hypervisor 1 to the 9 others, but not to the 99 others. That's how we do the replication.
The idea is for the replication is, so we replicate locally for the hypervisor. It could be /24 or /23. If it is more, you are exceeding our scale limits, right? So we have locally /24 or /23, which is not more than 500 hypervisors. And if you have more in another subnet, this is the VTEP subnet, the physical subnet, it will send just one packet to the destination, and it will be replicated there. So for scalability, if you have hundreds of such VTEP layer 2 networks, you will exceed our scale limits just from the hypervisor. So it's not a matter of...
I was just assuming that my PEPs are in very small subnets, let's say /27, /28.
Yeah.
And I just have thousands of them because I have 1,000 branches.
Yeah, but you don't need to replicate. I will take the multicast. Last question.
Yeah,
and
so
then,
it's valid question, but it will
let's
go
finish
beyond
this on a one-on-one. But we don't
scales,
replicate
right?
to all your hypervisors, because I bet all your hypervisors don't have a VM on that logical switch. Okay.
I think last
question, and then we'll stay here.
How do you deal with high availability of the edge?
How do I deal with the high availability of the edge?
We have cluster of edges, so you can have up to 8 edge, either a bare metal or VM per cluster. So, and when you provision T1 or T0 router, as I explained, the SR component, you can specify whether it is active standby or it is active-active. It is active-active, it will provision SR component, the centralized component, on every edge inside the cluster. So you can have up to 8 active-active SR components for the routers sitting on the edge. In that case, you need to configure uplink from every edge.
So, yeah, exactly.
Yes, and the switchover from HA event is really fast. We are using BFD between the nodes, and in theory it should be sub-second. In reality, it is 2 or 3. It takes 2 or 3 seconds to switch over. So, which is, I think, really good.
Okay, so thank you for your time, and if you have more questions, we stay here. Thank you.